Stanford University.
Let's begin with tonight's subject. Tonight's subject is grand unified theories, or SU5 in particular. There are many, many things that are called grand unified theories, and we're not going to study all of them. We're just going to take apart one version of it and see if we can see what it is that makes it tick, what some of its problems are, and if I have time to discuss the connection with supersymmetry, which does exist. I'll try to fill you in on what the connection is. The connection is not some deep thing that supersymmetry implies grand unification, or that grand unification implies supersymmetry. No, it's just if you put both of them together, you get a numerically better fit to certain things than either one by itself. Okay, so I should begin with a few words about group theory. Grand unified theories, whatever they are based on group theory. The group theory extends the SU3 cross SU2 cross U1 of the standard model. And it fits, or that group, SU3 cross SU2 cross U1, fits very comfortably into the group SU5, special unitary transformations acting on 5 complex variables. But before we do, I think we should say a few words about group representations. The particle multiplets form group representations. That means the symmetry groups act among them and scramble them up in various ways. And before you can start to classify the particle multiplets, you have to classify the representations of groups. Okay, so the representations of groups. Let's begin with let's start with SUN. Oh, incidentally, in the case of SU2, SU2 has to do with spin. Not the SU2 of the weak interactions, but the SU2 of the rotations of space. SU2 happens to be very closely related to rotations of 3-dimensional space. The simplistic statement that they're the same thing, and that's good enough for us. SU2 classifies the spin representations of particles, the angular momentum of particles, or the angular momentum of atoms, or the angular momentum of anything. And angular momentum comes in different kinds of multiplets. There's the singlet, which is sometimes just called a scalar because it doesn't transform under rotation at all, and that corresponds to spin 0. There's the spinner, which is the spin of the electron, half spin. That corresponds to spin 1/2. And there is a group representation of SU2 for every integer and half integer multiple of, well, for every integer and half integer. Spin 1, spin 3/2, spin 2, spin whatever comes next. 0, 1/2, 1. Well, the next one must be 1 1/2, huh? 3/2. 3 halves, 4 halves, 5 halves, 6 halves, 7 halves. Got it. Okay. All right. There are group representations, and they correspond to sets of objects that the group acts on and mixes them up. Okay. Let me just tell you a little bit about group representations, all that we'll really need. For SUN, the basic representation is called the defining representation, and it's just column vectors of n entries, 1, 2, 3, 4, up to the nth entry, altogether n units big. Complex entries, let's give them names. Let's call them psi 1, psi 2, psi 3, ... to psi n. And the group is described by matrices, special unitary matrices which act on these entries and mix them up. Psi prime, let's call them. Mix them up, multiply them by constants. You know what they do. OK, so that's the defining representation. And how many dimensional is it? It's n-dimensional. OK. Now, the first and simplest thing that you can do to the defining representation of SUN is to take its complex conjugate. In other words, take the collection of entries, psi1 star. Let's see, first of all, let's give these things names. This representation can either be called a defining representation or just the n. I cut out the word representation because we usually just say it's the n, or the representation of dimensionality n, which is acted on by the defining special unitary matrices. Now you take their complex conjugates, psi2 star dot 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 psi star n. The matrices which act, if psi is acted on to get mixed up by matrices, let's call them U, unitary matrices, then psi star is acted upon not by the same matrices, but by the complex conjugate matrices. So the psi stars actually transform in a different way than psi itself. They form a different representation. They form a different representation. It's called the complex conjugate representation. As an aside, I will tell you that if the states of particles transform under the n, then the states of antiparticles transform among themselves under the complex conjugate, which is called n bar, the complex conjugate representation. So first of all, we have the n representation, and we have, let's list some representations over here. There's the n, and there's the n bar, associated, if you like, with particles and antiparticles. OK, next, what else can you do?
Is that terminology used whether n is even or odd?
Yeah.
And does n refer to the matrices?
Yes, it refers to the size of the matrices, the size of the to the size of the defining representation.
I mean, and it also is a way of referencing the group itself.
Right. And for the defining representation, they're the same. OK. So the defining representation, if the group is SUN, the defining representation is n-dimensional, and the unitary matrices are n by n matrices. OK. Now you can construct more complex, and in that sense, to that degree, the n and the n bar are both n-dimensional representations, and it's a matter of complete convention which one of these you think of as defining and which one you think of as the complex conjugate of a defining representation. Closely connected with the fact that the antiparticle of a particle, the antiparticle of an antiparticle is a particle, so it doesn't matter which one you call particle and which one you call antiparticle. Once you name it, you stick with it, though. OK. The next thing you can do, let's suppose that these columns here represent the states, the possible states of a single particle. Again, they could represent the spin states, up or down. They could represent proton or neutron in what's called isospin. They could represent the three colors of quarks, red, yellow, blue, or whatever the appropriate degree of freedom is. All right, so here we have a particle over here, and it can have any one of n states. Let's put another particle in right next to it. How many states are there? And we're only thinking now about the internal quantum number associated with the group SUN. We're not thinking about its position, its momentum, or even its spin right now. If this particle can be in any one of n states, how many states can the two particles be in? It's quite clear. It's n squared. All right? So there must be an n squared.
Minus 1?
No.
Pi by 2?
No.
No, I'm saying that n squared would require superposition. Would it require superposition?
Superposition of what?
Violation of the exclusion principle.
No, it's like this particle is over here, and this one is definitely over here. They're in two different locations. We're just trying to do the mathematics of group theory by pictures, okay? So they're definitely at different locations on the blackboard. There's no question of them being in the same state because one of them's nailed down over here and one of them's nailed down over here.
I'm saying if there's a fixed number of states and one of them's occupied.
Being in two different places is a change of quantum.
Right. The Pauli exclusion principle would say you can't put two particles in the same state, but being in the same state entails not only these internal quantum numbers, but being at the same place. All right? Now, I explicitly tell you, they're not in the same place. One of them is here, and one of them is there. Once you say that, there are no further constraints of the Pauli exclusion principle. They are not in the same place. They don't exclude each other in any way. All right. So this one's over here. In fact, it could even be different particle types. These could be one set of particles. This could be another. But it just happens that they transform under the same n-dimensional representation. All right, so how many states then, just with respect to this SUN, not with respect to their position, angular momentum, or other interesting quantities, but just with respect to this n-ness, let's call it the n-ness of the particle, how many states there are? It's clear, there are 25. And that's correct, 25 such states, n cross n times n squared. Okay, now, you could label the states. If you label the states of one particle as psi I, you could label the two particles system as psi ij. Psi ij. If psi I runs from 1 to n, then psi ij runs from 1 to n squared if you let I and j run over the n squared possibilities. So, for example, there would be the state psi 1, 1, in which both particles are in the one state. There would be psi 1, 2. Psi 1, 2 would be this particle in state 1, this particle in state 2. There would be psi 2, 1. That would be the opposite. This particle in state 2, this particle in state 1. Again, no exclusion principle is operative here. And so there are n squared possible entries. How do you transform these things? You transform them by thinking of the I index and the j index separately rotating under the group. And in fact, an even simpler way to think about it is to think of this as a product. Psi I, let's call it phi j. This particle is described by psi, this one by phi. It's got n squared entries. And how does the group act on this collection of things? By acting on psi and phi separately, rotating psi and rotating phi. All right, so that defines an n squared dimensional representation of the group. But that representation is not irreducible. Now, what is irreducible? That's a new word. What does irreducible mean? What it means is that there are certain combinations of psi ij which transform among themselves and don't get mixed up with other combinations, certain linear combinations which transform among themselves and don't get mixed up with the other with the other combinations. They can be pulled aside and thought of as a now I'm going to give you an example in a moment, but let's just talk about what this would mean for ordinary spin. We have two spin states, each one labeled by either up or down. All right, so we have altogether 4 states, up, down, up, down. We have up, 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 down, up, and down, down for spin. I'm not talking about up and down quarks. I'm talking about spins pointing up and spins pointing down. All right, now, these are 2 half-spin particles. If you combine 2 half-spin particles, there are 4 possible states. But the 4 possible states form among themselves multiplets. What are the multiplets that the 4 states form, you know? One combination is a singlet, and the singlet corresponds to 0 spin. And the other combination is a triplet of states, which form spin 1. A spin 1/2 and a spin 1/2 can form either spin 0 or spin 1. How does one understand that from the point of view of psi ij? All right, so I'll tell you right now, psi ij, thought of as a function of 2 spins, can be either symmetric under interchange of I and j or antisymmetric. Of course, it could also be a linear combination of symmetric and antisymmetric. But let's consider all psi ij's which are symmetric, so that if you interchange I and j, they become the same thing. How many independent configurations is that? Do you know? 3. 3 linearly independent combinations that are symmetric. I can tell you what they correspond to. They correspond to up, up, that's symmetric, down, down, and 1 over square root of 2, up, down, plus down, up. Those are the 3 which are symmetric with respect to interchange, and they have the property that when you act with the group SU2 on them, they mix them up among themselves, but do not mix in the last one being 1 over square root of 2, up, down, minus down, up. The antisymmetric combination. So this is the symmetric combination. And how many states are there? Linearly independent ones? 3. A spin 1 multiplet. So when you take 2 half spins, one way of combining them can give you spin 1. And the other way is unique. There's only one antisymmetric combination. It's up, down, minus down, up. It's a singlet. And that means it just doesn't transform under the group at all. It's a scalar with respect to these group rotations. And that gives you the 0 spin combination. So this is a pattern. You can take objects which transform as not as an n and an n bar, but as 2 n's. Well, n bar, okay. We can call that n cross n. Psi ij is an object which lives in the n squared or n cross n. The cross here simply means we're combining 2 systems, the n cross n. But we can take the symmetric combinations and the antisymmetric combinations. They do not mix with each other. The group operations do not mix the antisymmetric and the symmetric. So there is symmetric and psi ij antisymmetric. We'll count later how many of them are there of each kind. I'll let you do the counting. It's not too hard to count. I can't remember offhand. This is usually a smaller representation than this one. Psi ij symmetric and psi ij antisymmetric. And those are 2 distinct representations. Okay? So the next thing we have is n cross n symmetric and n cross n antisymmetric, let's call it. We're going to see some examples of this kind of thing. We're going to work it out for SU5 and see what kind of representations they have. All right. Next, we've already said that you can take that there's a complex conjugate representation that could correspond to a particle. And instead of putting two particles down to study, we could put a particle and an antiparticle. Let's put a bar over it. A particle and an antiparticle. This is different than a particle and a particle. The question is, what's the group theory, or what's the representation that describes a particle and an antiparticle? How many states are there? N squared again, right? Exactly n squared. And again, there are two ways of combining them. Well, there may be more than two ways of combining them. But no, there are really n squared. You can combine them, again, symmetrically or antisymmetrically. No, you can combine them. I'm sorry, I take that back. All right. If you take these two things, and you write a, let's give a different label to it, because it's not in the n squared, it's in the n cross n bar. But there are still n squared independent elements. They again are described by some matrix, Mij. This is also a matrix, psi ij. Right. This is a matrix, but you discover when you start thinking about or working out the transformation properties that there really are only two independent combinations, one of them being the traceless combination, and the other being everything else. We've seen this before. We've seen it in SU3, where I told you that, that there's a representation of SU3 which is of SU3 which is 8-dimensional instead of 9-dimensional. A particle, a quark and an anti-quark, have 9 possible states, but those 9 possible states can be in a singlet, and the rest of them correspond to trace equals 0, or m trace of this equals 0. And those form what is called the adjoint representation. The adjoint representation has dimension n squared minus 1. For SU3, n squared minus 1 is 8. All right, we've seen how that corresponds to the 8 gluons of quantum chromodynamics. For, what is it for SU2? It's called the adjoint. What is the adjoint representation for SU2? 3-dimensional, and it corresponds to spin 1. For SU3, it's 8-dimensional. It's called the adjoint representation. But that leaves one more linear combination, namely just this 1. That's a singlet. That's a state which doesn't transform under the group at all. All right? So this is all we need to know about group representations, that there's the representation n, which is the fundamental defining representation. There's the representation n bar, which is the complex conjugate. And you can multiply them together, which is really just the act of putting down different numbers of particles and antiparticles, or group theoretically it's that, combining the representations together, and then sorting out and finding which combinations will transform into each other under the group, so separating the transformation properties into different representations. And that is the process, for example, of taking 2 spins and discovering that they can form spin 0 or spin 1, a 3-dimensional representation, or a 1-dimensional representation. This is spin 0 is the 1-dimensional representation. In SU3, similar kinds of things. SU5, the same kind of things. Now we're going to see how this works by explicit example. The group that we're interested in is SU5. SU5 mixes up 5 objects, which I don't know what to call them. Let's call them just the fermions. Which fermions we'll see in a moment. The fermions belonging to a single family. There are 3 families of fermions that are known, and only 3 is probably correct. I'll just remind you what the first family consists of. It consists of 3 quarks, well, 2 quarks up and down, but each up and down quark comes in 3, or each quark comes in 3 colors. So this is red, yellow, blue, red, yellow, blue. Also, there are the leptons, the electron, and its corresponding neutrino. There's a neutrino for each lepton type. And this pattern gets replicated 3 times, and we'll just refer to one of these families, sometimes called families, sometimes called generations, one of these families at a time. Nobody has a unified theory of how to unify together the different replications of the same pattern. That is completely beyond us. We don't even know what it means. Not what it means, we know what it means, but we don't know how to understand why it's so. So let's just focus on such a combination of particles here. All right, so what are the 5 entries? It's easiest just to write down what the 5 entries are for the defining representation, and then explore a little bit about it. Just as you would put for SU3, you would put red quark, yellow quark, and blue quark, the 3 entries. That's what gets mixed up by SU3. Then SU5 mixes up neutrino, electron, which I'll write as E- to indicate that it's a negatively charged electron, and the 3 down antiquarks. Which 3? The 3 of the 3 colors. Now, this is a bizarre thing to combine together, but as you'll see, it makes a lot of sense. These are quarks, or antiquarks to be specific, and only the down antiquarks, neutrino and electron. They form a multiplet under the group SU5. And what is the group SU5? It's just the 5 by 5 matrices which mix these things up among themselves. In other words, transformations which can take neutrino to electron and electron to neutrino. Well, we've seen those already. Those are the SU2 of the weak interactions. The SU2 of the weak interactions mix neutrino with electron. And what about the things which mix the anti-d quarks? Well, that's just a color group. Red, yellow, and green. So the transformations which mix up these things here, that's just color, quantum chromodynamics. But now we have some new possibilities, and we're going to have to explore those. Transformations which take neutrino to anti-down quarks, electrons to anti-down quarks, and so forth. Something new. Now remember that for each one of these mixing ups, let's call them, there's typically a gauge boson which allows transitions between them. The gauge bosons which allow one d quark to go to another d quark or d bar quark, what are those gauge bosons? The gluons. What about the gauge bosons which take electrons to neutrinos and back and forth? Those are the W's. All right? And so this is the corner here that corresponds to weak interactions, and this is the bigger corner that corresponds to, this is SU2 here and SU3 here. Where U1 is hiding, we'll come to, I hope we'll come to it, we'll see. We'll see. Okay. All right, so this is the defining representation. That's very strange. There's no up quarks. Where's the up quarks? One other point, which I mentioned last time, is we always treat the particles as left-handed. Okay? Left-handed particles. Now, what about the right-handed particles? The electron, the left-handed electron comes together with a right-handed electron. Well, the answer is that if a particle is left-handed, or if a particle is right-handed, its antiparticle is left-handed. So we can always enumerate the particles by enumerating only left-hand particles. For example, if we were enumerating the electrons, we would enumerate not electron and positron, but the left-handed electron, let me just put a little L next to it, and the left-handed positron. The left-handed positron. The antiparticle of the left-handed positron is the right-handed electron. This is just a notational device or a way of enumerating particles, but it's useful because these groups that we're talking about do not turn left-handed particles into right-handed particles and so forth. So we keep track of the particles as left-handed. We don't miss any that way. We just have to remember that when we're looking for the antiparticle, for example, the d quark, the anti-d quark, this is the anti-d quark. But the left-handed, these are all left-handed, and they form the basic left-handed representation of SU5. Now, where are all the other particles? In fact, we probably ought to write down what they all are. All the left-handed particles. Let's list them. There's the left-handed neutrino. That's the one we see in weak interactions. There's the left-handed E minus. There's the D bars, 3 of them. Okay. Then there's the left-handed E plus. This is no particular order here. I'm just writing them all down. There's the left-handed positron. What about the left-handed D quark? D, D, D. 3 colors of left-handed D quark. And what am I missing? I'm missing the up quarks, the left-handed up quarks, up, 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 and also the left-handed anti-quarks, up bar, up bar, up bar. Let's see if I have everything. I have electron and positron. That's good, left-handed. I have D bar quarks and D quarks, and I have up quarks and anti-up quarks. What's missing is an antineutrino. Okay, we're going to come to the question of antineutrinos, but I will tell you this. The standard model, the pure form of the standard model, does not have an additional, let's call it left-handed antineutrino. The left-handed version of the right-handed version of the neutrino is the antiparticle of the left-handed. There's a left-handed neutrino and a right-handed antineutrino. There is no right-handed neutrino and whatever the missing one that I didn't say was. Yeah, okay. This is the collection of fermions in the first family of the standard model, and that's all there is. Okay, so let's see which ones we've captured in the 5 here. Neutrino, electron, down, down, down. That's it. Okay, now why did I group the down quark there?
I have a question.
Yes.
You had mentioned that fermions get their mass from oscillating, changing.
Left to right, yeah.
And does that mean it also changes into an antiparticle while it's?
No, it changes into the particle of the same. Okay. Depends on whether we're talking about neutrinos or the other particles.
Say an
electron. No. Electron turns into an electron. Left-handed electron becomes right-handed electron. Otherwise, it would violate charge conservation. If a left-handed electron, if an electron became a positron, something bad happened. Charge disappeared.
So, but that doesn't seem to fit into this picture so far.
We'll come to it.
Okay.
We'll come to it. Right. But the mass is a transition between left-handed and right-handed particles of the same charge, okay, of the same electric charge. Now, only the neutrino doesn't have an electric charge. So it's the only one which conceivably could have a transition from neutrino to antineutrino. But we'll come to that. This has to do with neutrino masses. Okay? In the standard model, incidentally, the neutrino is strictly massless. Okay. Which is not the experimental fact. The experimental fact is neutrinos have very, very small masses, extremely small, right? Measured in fractions of electron volts, so they're very light. Okay, the question now is where, well, let's see, do we want to say anything else about this? Yeah, let's think about the transitions which can happen between these particles by virtue of emission and absorption of gauge bosons. Now, we're talking about SU5, which is bigger than SU3 cross SU2 cross U1, so there may be new kinds of gauge bosons. First of all, there are the various transitions or interactions that take place just among these two. An electron can become an electron, for example, if it emits a neutral gauge boson. A neutrino can become a neutrino if it emits a neutral gauge boson. And an electron can become a neutrino if it emits a W minus. So in here, we have the weak interactions. The weak interactions, the emission and absorption of W, Z, and also photons. The electroweak theory. That's what's occurring in this block in here. And here we have d-bar quarks becoming d-bar quarks. Perhaps the third one here makes a transition to the second one, or whatever. And that means the emission of gluons, which we also learned to think about in a slightly different way. Think of the gluon that's emitted. The d-bar quark goes through. The d quark here, when it turns around in time, I'm using a metaphorical language. When it turns around in time, it becomes a d quark. And so the quantum numbers of the gluon here have the quantum numbers of a d-bar system, of a particle and an antiparticle. Okay. In other words, they belong to, with respect to SU3, where did I write it? N cross N bar, the adjoint. The n squared minus 1 members of the adjoint. The gluon is an object which lives in the adjoint representation. The quark, or the antiquark in this case, belongs to the three-dimensional representation of SU3. But there are new things, new kinds of gauge bosons that have to exist now if we're going to try to unify SU3 cross SU2 cross U1 into SU5, namely transitions which take D, anti-Ds, let's draw that, an anti-D to an electron, let's say. This would be the emission of something. What would the charge of that thing be? Let's see, D bar has a charge of 1/3. This one has charge of -1. 4/3, right? 4/3 or -4/3? 4/3. 4/3. This would have a charge of 4/3. And I can never remember whether this one is called the X or the Y boson. It's one or the other. I do not remember which. There are X bosons. I think this one is the X boson, but I cannot remember. There's an X and a Y. And the Y is the thing that takes the D bar and makes a neutrino out of it. What is its charge? Yeah, 1/3. 1/3. Charge 1/3. I believe that's called the y, but I may have x and y backward. I don't remember. I meant to look it up before class, but I forgot. All right, so there's the x and the y boson, which are the new gauge bosons, which take quarks and make leptons, or leptons and make quarks. There is also the antiparticle of the X boson, which has charge -4/3, and the antiparticle of the Y, which has charge -1/3. Okay? Those are the new things we're going to have to contend with, understand what they do, and understand what the potential new kinds of interactions are because of this possibility. Okay? New kinds of things in nature. Do they disturb everything we thought we knew about physics? Well, yes, they do, but we'll see. All right, so that's the gauge bosons, and the gauge bosons live in the adjoint, which is the n cross n bar, but the piece of it which has trace equal to 0. In other words, the piece of it which has dimensionality n squared minus 1. If you're not comfortable with this n squared minus 1, just ignore it. Just n squared will do. Okay, it's close enough to the truth. It will give you one extra particle, 1 out of 25, big deal.
So are there 3x?
Good. The that's right. The X bosons and Y bosons have color. Why? The d particles, the d quarks or d bar quarks have color. The electrons don't. And so to conserve color, the X bosons and the Y bosons must have color. That means that they themselves can emit and absorb gluons. They, like the quarks, are strongly interacting things which combine together by gluon exchange and so forth. So these particles are among the particles which carry color, and like quarks, they are never completely released freely in a reaction. They always come together in combinations with quarks or with other things or with themselves that have integer charge. All right, so they're just like quarks in that respect. All right, but we're missing more than half the fermions. Where are we going to put them? Well, we could put them in another one important point, yeah. One important point. Electric charge. The quantum numbers of particles in a theory like this are related to the generators of the group. The generators of the group are the traceless Hermitian matrices, the n by n traceless Hermitian matrices, which in fact are in one-to-one correspondence with the adjoint representation. The generators of the group are traceless Hermitian matrices. How many independent traceless Hermitian matrices are there of dimension n?
N squared minus 1?
N squared minus 1. So actually the generators of the group are in one-to-one correspondence with the adjoint representation. And in fact, the generators of the group are intimately connected with gauge boson emission. One of the generators of the group has to be associated, must be the quantum mechanical operator, which represents electric charge. Electric charge is one, since photons are included among the things which can be emitted here, we are talking about a theory that contains electric charge among the generators of the group, or among the quantum numbers associated with those generators. Now, there's only one thing that you need to know to understand why I put d bar there instead of something else, and that's that the trace of the generators is 0. The trace of the generators is always 0. The implication of that is that the sums of the charge, or the sums of the quantum numbers within a given representation, always add up to 0. That is a general rule for SUN groups, for groups which are defined in a way which the generators are traceless. have zero trace. The generators having zero trace, what was that connected to in terms of the unitary matrices? That was their specialness. Specialness means determinant 1 for the U's. That means trace equals 0 for the generators. Trace equals 0 is another way of saying that every quantum number that's described by this group within a given multiplet must add up to 0. Okay? Supposing I had put the d quark here instead. All right, let's add up the charges of all the entries. Charge 0, minus 1, minus 2. D bar has charge minus a third. Okay? Doesn't work. Doesn't work. You could not embed the electric charge into the generators of SU5 if you tried to put D here. Put D bar, electric charge of minus 1, and then 3 times plus a third. So the charges add up to 0. Okay. That is a mathematical, well, it's the mathematics of why I put D bar here, in order to get the sums of the charges to add up to 0. Okay, now let's talk about, well, okay, let's talk about now the other fermions which we left out so far. Let me show you how to construct another representation. This is just a bit of gymnastics to do the group theory in a simple way. Right, to do the group theory in a way that, that's easy to explain. What you do, you could try to build representations. This is the N, or this is the 5-dimensional representation, the defining representation. We could start taking things like 5 cross 5 and see what we get. It would be a good thing to do, but I'm going to do something slightly different. I'm going to begin with the 5 bar and multiply it by the 5 bar. All right, so what's the 5 bar? The 5 bar is the collection, is the column vector describing the antiparticles of this collection. This is the 5. Let's write down what the 5 bar is. The 5 bar is just the antiparticles. Antineutrino, electron, D, D, D. Let's not worry about the handedness. We're not worrying about now handedness. We're only worried, or only thinking about group theory now. Just, this is a trick for doing some group theory. All right, now let's consider 5 bar cross 5 bar. E plus, sorry. E plus. Antiparticle. We're just, as I said, we're just doing some mathematics now to see how group representations combine. Let's consider the 5 bar cross the 5 bar. 5 bar cross 5 bar. To describe it, we could make a matrix. We could make a matrix of entries. I'll show you how to do it. These are going to be 5 by 5 matrices. But I kind of want to separate the 5-ness into 2-ness and 3-ness. So let's put some partitions here. These are 2 by 2. This is 3 by 3. This is 2 by 3. This is 3 by 2, okay? Just to guide the eye. And let's make some labels. This is 5 bar cross 5 bar, so we should label horizontally across here. I'm going to put exactly what I see here. Neutrino, electron plus, D, D, D. Neutrino, electron plus, D, D, D. 5 bar cross 5 bar. And also, I also want to partition these things up so that I One, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now imagine This is only to be imagined. It has nothing to do with the truth. But let's suppose I made some composite objects. In each one of these entries, I will put a composite object which has the quantum numbers of the row and the column. And let's see what kind of objects you make. Oh, sorry, one more thing. One more thing. Remember I told you when you take the n cross n representation, you can take it symmetrically or anti-symmetrically. Same thing with the n bar cross n bar. Symmetric combinations or anti-symmetric combinations. We're going to take the 5 bar cross 5 bar anti-symmetric. Anti-symmetric. Anti. All right. The first implication is that we put zeros on the diagonals. That means there will be no particles in this representation with quantum numbers that belong on the diagonal. Secondly, the lower half triangle, it just replicates the upper half triangle with a minus sign, so they're not independent objects. They're the same things except with a minus sign. They're not new particle states. All right? The only independent particle states go here, 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 and here, and here. Let's see what their quantum numbers are. In particular, the electric charge. All we need is the electric charge. The electric charge which goes here will be the electric charge of a neutrino plus a positron. What particle has the quantum numbers of the quantum numbers now just mean electric charge. What particle in the table of all of these have the electric charge of a neutrino and a positron? A positron. Neutrino is neutral. So over here, in this place, we put E plus. Now, always the left-handed particle. This was a trick to construct some group theory, but we will always be talking about left-handed particles. All of this is left-handed. Okay, what about a neutrino and a down quark? Neutrino is neutral. So let's put here down quark, down quark, down quark. The 3 colors of down quarks. Incidentally, this here, it was just an auxiliary construction. We're not putting particles into the 5 bar. This was just an auxiliary construction so that I could show you what the 5 bar cross 5 bar looks like. Let's erase this so we don't get confused. Okay, what particle has the electric charge of a positron and a d quark?
X.
Which one?
An X?
No. Among the fermions. The fermions. Here we're just talking about the fermions. No, we're talking about the fermions. What particles have the quantum numbers of a down quark among these here? This is all we're talking about now. We're trying to construct the... is it up bar? No, I think it's up. Up. Charge 1 minus 1/3 is 2/3. That's the up quark. This is 0, not U. Okay? What about a down quark? What about a down quark and a down quark? It's 2/3. No, it's minus 2/3. Down quark has charge minus 1/3. This has charge minus 2/3. What's it going to be? Anti-up quark. Same thing here and same thing here. That's it. That's it. We filled up all the boxes and we filled up this entire collection here. Okay. So, and incidentally, how many independent states are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A 5 cross a 5 is called a 10. A 5 bar cross a 5 bar is called a 10 bar. So the statement is that this entire collection of particles has the structure with respect to its quantum numbers of a 5 and a 10 bar. This is actually a rather remarkable fact that, that the particles fit so neatly into representations of SU5. You may find it a little bit awkward that half the particles belong to a 10-dimensional representation, not half the particles, 2/3 of the particles belong to this 10 bar, the other third belong to the 5. There is a bigger unification that's possible into a group which is bigger than SU5 but contains SU5, and it's called O10. All of these particles are in one representation of O10, but you have to add one more particle in O10, and it's the antiparticle of the neutrino. But we're not going to, if we get to it, we'll get to it. But for the moment, this is what's called SU5 unification of particles. Okay, any questions up till now? Yeah.
In the SU5, particles are there in the column matrix.
Well, this set of particles are there in the column matrix.
Yeah.
This set of particles are in an antisymmetric matrix.
In the 10 bar, what's the column matrix?
What's the what?
What is the column matrix?
Oh, just take these in any order that you like and line them up vertically. It's better to think of it as a matrix. It's better to think of it as a matrix, but there's nothing to prevent you from taking them and lining them up into a 10-plet. But the transformation matrices which act on that 10-plet are not the full set of SU10 matrices. It's a smaller set of matrices than that. But it's better to think of it as a matrix. When you start combining representations together, you can always think of them as columns, if you like, just by taking them and just laying them out in a column. But it's often much more convenient to think of them as matrices that transform as matrices rather than that transform as column vectors. All right, so this is the breakdown of the particle multiplets into a 5 and a 10 bar of SU5. Now, yeah.
In the third row and the fifth column, why is that up and up?
Third row, oh, whoa, sorry, up bar. Yeah, thank you. Right.
I also omitted the colors. I assume color is conserved?
Color is conserved. Right. Color is conserved.
In particular, where you have D bar, D bar, D bar in the columns, is one of them red, green, blue, or is that?
Yeah, red, green, blue. This could be the red, green, blue, red, green, blue, red, green, blue. Now, what happens if you combine together a green quark with a blue quark? You get something anti-red. Well, so you would get an yeah. So let's see. So these anti-quarks here are, let's see, red with green would be blue, red with blue would be green, and the green with blue would be red. Okay. That's the pattern of SU5. Any other questions? Now, this is quite extraordinary when you think about it. You're putting into one multiplet, one symmetry multiplet, quarks, left-handed up quarks, and left-handed anti-quarks into a single symmetry structure. Left-handed up quarks and left-handed antiquarks, up quarks. On the other hand, the d quark, its particle and antiparticle, left-handed particle and antiparticle, belong in different representations. Same with the positron and the electron. The left-handed positron and the left-handed electron are in different representations. And there's the neutrino sitting all by itself in the 5 with no counterpart associated with an antineutrino. That is the particle content, or the fermion content, of the Standard Model. Okay, now let's see, maybe we should take a 5-minute break here. Yeah.
You can transform within each of these, but that means there's no way to get from the d bar across.
The Higgs boson does that. The Higgs boson does. The Higgs boson cuts across here. The various kinds of Higgs bosons can cut across here. They can take left to right, and that's sort of what's going on here. But let's take a 5-minute break. Let's talk about the various gauge bosons. The various gauge bosons correspond to the transitions between these 5 objects. All right. The same set of gauge bosons, actually they're antiparticles. Gauge bosons in general have charge. W's have charge, X's and Y's have charge, so they also have antiparticles. The gauge bosons mix up these 5 entries. Okay. For example, between here and here, we have the Z, the W, and the photon, which act in here. And in here, we have the gluons. The new things that we have now are the X and Y bosons, and the X and Y bosons take you this way. That's X. As I said, look it up. I can't remember which is X and Y. But, and Y bosons, according to my present convention, take you from d bar quarks to neutrinos. Those are the transitions which happen by emission of these particular gauge bosons. Okay. How do those gauge bosons act among this 10 bar? In other words, when a gauge boson is emitted by one of these particles, which one does it become? Now, the way to think about this is that the gauge bosons can be thought of as shifts. In the case, some of the gauge bosons don't do anything. The photon, for example, takes an electron to an electron. So that's a kind of trivial shift, which doesn't take you anywhere in this column. The Y bosons shift you up or shift you down. And the gluons shift you among red, yellow, and blue, so forth and so on. So think of them as kind of shifts, which shift you around in this space. Okay, what do those same gauge bosons do acting in this multiplet? And the answer is that they either take you horizontally or vertically according to the same pattern. For example, the emission of a gluon can take you this way, or the emission of a gluon, here's gluon, gluons are down here. It can take you this way, or it can take you this way. That's the rule, that whatever the various gauge bosons do, the shifts that they make, the same thing is repeated here, except that it can happen, you can either emit a gauge boson and go horizontally or vertically. Another way to think about it is to pretend that these entries here really were composites of pairs of particles, or pairs of antiparticles to be specific. One of the particles or antiparticles represents the horizontal direction, the other represents the vertical direction, and a gauge boson could be emitted from one or the other. If it's emitted from one, it takes you horizontally. If it's emitted from the other, it takes you vertically from one entry to another. So let's see what the weak interaction gauge bosons, the Z and the W, for example, do. Well, they shift you in this upper 2 slots here. So that means, let's think about what they do horizontally. Horizontally, they take you from this column to this column. Moving horizontally, they take you from this column to this column. Well, there's not much here to do. The E plus doesn't do very much. Okay, but they can also take you vertically from this neutrino slot to this positron slot, which means they can take you in this direction, down to up. Well, that's something that that's something that the W boson does. The W boson does take down to up. The down to up of the W boson is the source of beta decay. A down quark becomes an up quark, or an up quark, in fact, yes. A down quark becomes an up quark inside a nucleon, takes a neutron to a proton. So the emission of a W boson can take a down quark to an up quark. That's going vertically here. The color group acts among red, green, and blue. It can act horizontally here, taking a down quark to another color of down quark, or an up quark to another color of up quark. But it can also act vertically here, taking this to this, and that mixes up the 3 U bar. It can take green to red. Supposing you want to take blue to red. How do you take blue to red? Well, you go over to here. Let's see, where are we? Remember, this is really an I haven't put in the entries over here. The entries over here are just the negatives of the entries over here. If I wrote them down here, we could go from blue to red on this side directly. But okay, you can go this way or you can go this way. And that's color acting on the U bar quarks. All of this is the same as in the standard theory. Nothing new here. The new things that I want to get at is what the x's and the y's do. What do the x's and the y's do among this column here? Okay, we know what they do. They take, for example, the X boson can take, and its antiparticle, take this entry to this entry, if you like. All right? That's, what is that? That's taking this entry to this entry. In other words, the emission of an X boson can take a D bar, here's a D bar coming along, emitting an X, and becoming an electron. That's over here, the left-hand, these particles. But exactly the same kind of emission can take place, let's see, between, this is the second to the third, so it's 2 to 3, namely positron to down quark. Positron to down quark, which in terms of this constituent model over here, just takes this positron to a down quark. That's the anti-X being emitted. The anti-X being emitted takes positron to down quark. What else can happen? Did I get that right? Positron to down quark? Let's see, what can it do? Yeah, I guess that's down quark to positron, yeah. Or down quark to positron, or the antiparticle positron to down quark. In that way, you can figure out what the various emissions of X and Y bosons. Let's have it the Y boson. The Y boson takes the first entry to the third entry. All right, the first entry, where's the first entry person over here? First entry over here to third entry takes a down quark to an anti-up quark. Down quark to an anti-up quark. Also over here, down quark to anti-up quark. Sometimes it helps to fill in the rest of these columns and slots over here. Takes down quark to anti-up quark. So just go through it, play a little game of figuring out what the X boson, what kind of transitions the X boson and the Y bosons make. But they do exactly the same thing among these columns and rows over here as they do over here. Right? They take, for example, first entry to third entry. First entry, whereas first entry, there's nothing here, can't go here. First entry to third entry. First entry to third entry. That means there are new kinds of processes, and one of those new kinds of processes is very, very surprising. So let's look at what the new process is.
What about the fourth and fifth entries?
The fourth and fifth entry, those are the emission of gluons. So 4 to 5. You go from a blue quark to a green quark by...
From the first to the fourth entries on a...
First to fourth. First to fourth.
That would be a Y.
Yeah, that would be a Y. Right. That would be a Y boson. Right, so a fourth, the Y boson can take down to anti-up. The X boson can take up to anti-up, I think. Yeah.
Can you just fill in just one box of the anti-symmetric entry?
Yeah, minus E plus, minus D, minus D, minus D, minus U, minus U, minus U, minus U bar B, minus U bar green, and minus U bar red. The hell did I do it? Where? Here? Yeah, okay, right. That's the rest of the table. Now, it's redundant. If a process can take you from one place to another here, it'll do the same thing up here, going rows instead, just interchange rows and columns. So it's redundant to keep track of these, but you can draw it if you like. Okay, so let me show you a process which is unusual. The down quark can go to a positron. Down quark to positron, positron back to down quark. What boson, which is the boson which is emitted in that process? X. So an X boson is emitted. And what's the charge of the X boson? Is it 4/3? Yeah, 4/3. No, minus 4/3. In this case, it's the X minus 4/3, which is the antiparticle of the X that we were talking about before. All right, so we can call it an anti-X. All right, but the X can also do something else. Now let's see if I can figure out what. It takes the first element to the second element to third element, let's say. Second element to third element. So here's a second element in the column, and here's a third element in the column. Here's another process it can do. It can take up to anti-up. It can take up to anti-up with an X boson over here, but now is this an X boson or an anti-X boson coming in? Oh, it's an anti-X boson coming in. Let's check that. This had charge minus 4/3, right? It went from minus 1/3 to plus 1. This must have had charge minus 4/3. Now we take minus 4/3 add it to 2/3, and we get minus 2/3. All right? So here's two processes that can happen involving the X bar. Both of them possible according to this theory. Let's put them together. We put them together, and we have a process in which down quark becomes positron, emits an X, and that X now grabs a hold of a U quark, which then becomes an anti-U quark. Well, that's interesting. But now let's add one more particle, which is pretty much just a spectator in all of this, another U quark. A U quark does nothing, just becomes a U quark. There's a process which takes a D quark and two U quarks. What's that called? Proton. This is a proton. It's just proton. And creates out of it a positron, same charge as the proton, and a U anti-U quark. What kind of particles can you make out of a U and an anti, or a quark and an anti-quark? Mesons. In particular, pi mesons. This would be a neutral pi meson coming out of here. Pi naught. A neutral pi meson. So we've discovered, or not discovered, but we've postulated, in doing this, we've postulated something unusual, namely a process where a proton, if we just take a black box view of it, proton becomes positron and a pi naught. Another thing that could happen is the U quark and the anti-U quark could annihilate and make a photon. This would be a little less likely because there's an extra factor of the fine structure constant in the probability, but that's another process that can happen. Proton becomes positron and photon. Now, this is potentially a very, very dangerous game. If protons had a habit of just decaying to become positrons and photons, or positrons and pi naught, needless to say, we wouldn't be here. Our nuclei wouldn't be here, hydrogen wouldn't be here. So this is a rather dangerous process. It's called proton decay. And proton decay is a consequence of pretty much any kind of attempt to unify the weak interactions and the electromagnetic interactions and the strong interactions into one group. SU3 cross SU2 cross U1 is, of course, one group, but it's a product of smaller groups. To unify it into one non-product group, a bigger group. Almost any, in fact, every unification that I know of which tries to put these particles together into a single multiplet, or which tries to put SU3 cross SU2 cross U1 together into a bigger symmetry, always has proton decay as one of its consequences. All right. This is very dangerous, not something that we would want to happen to us, and certainly not something we would want to happen quickly. Yeah.
The coupling constant for producing X bosons, is that the same as the coupling constant for the whole group?
Yep. Yep. And it's basically just the fine structure constant. You have the product of two coupling constants, one over here and one over here. Not different. Numerically, it might be a little bit different for a number of effects, one of which we may get to talk about. But numerically is not the important thing here. The order of magnitude of these coupling constants is the same as the usual coupling constants. Why? Because they all belong to the same structure. They belong to the same structure, and in this SU5 theory, there's only one coupling constant. The coupling constant for the emission of a gauge boson. Why they wind up being different in our laboratories is something we either may or may not have time to discuss tonight. But yeah, the order of magnitude of these coupling constants is just usual coupling constants. The same coupling constant which governs the decay of an atom when it de-excites, the same coupling constants which govern beta decay, same coupling constants that govern all the ordinary particle physics decays. So the question then is why this doesn't happen in the blink of an eye as fast as other particle decays. All right. Answer, or potential answer, not the answer because we've never detected these and we don't really know that it's a real process. But what leeway, what do we have available to manipulate to slow down the rate of this? The mass. Okay. The mass of the X boson goes in here, and it goes in the form of a propagator. Propagators always look like 1 over m squared. They may have some momentum dependence also, where the momentum dependence would be the recoil momentum, but that's generally small potatoes. The important thing in the denominator here is the mass squared of the X boson. That would be one of the elements, and then you would have a product of coupling constants, let's say a G times another G, G for coupling constant, G squared of some sort, divided by X by mx squared. Now, if you sat down and calculated the Feynman diagram for this, which is a reasonably simple Feynman diagram, this is what you would get, times some number. Okay, the Feynman diagram gives an amplitude, gives a quantum mechanical amplitude for a process. How do you calculate the probability for the process? You square it. Okay, so there will be a g to the fourth and an mx to the fourth in the decay rate. The decay rate is the probability per unit time that the proton decays in the decay rate. The question is, how big do you have to make mx in order that the decay rate of the proton is slow enough so that it doesn't conflict with experiment? Question then is, what is the half-life of the proton? This is the decay rate inverse to the half-life of the proton. Turn it upside down, it becomes there's other factors in here, factors of the mass of the proton and so forth, but this is the important thing. If we measured everything in units of GeV, the mass of the proton, this would be the decay rate, approximately, order of magnitude. So how big do we have to make mx in order that the decay rate is long enough? That raises the question, what are the bounds on the lifetime of the proton? All right, there's all kinds of bounds. The proton is clearly longer lived in the universe. There are still protons around from the Big Bang. Okay, so the proton, first of all, the proton has to be longer than the age of a human being, otherwise we wouldn't be here. It has to be longer than the age of the universe, otherwise they wouldn't be here to make us. So 10 to the 10th years, 10 to the 12th, 10 to the 14th, 10 to the 15th years for sure. But now there's questions of experimental data. You can't wait around for 10 to the 15th years to see a proton decay, but you can start with 10 to the 15th protons. That's not a lot of protons. It's a small amount, a very small sample of protons, and see how often a decay takes place. With 10 to, if the decay rate for a proton, if the half-life for a proton was 10 to the 15th years, then if you start with 10 to the 15th protons, you ought to see 1 decay per year approximately. 1 decay per year. A proton decaying is something which can be detected in the laboratory, even among 10 to the 15th of them. Not that this is easy. This is really easy stuff. Seeing a proton decay in a sample of 10 to the 15th protons, and you don't see any decay. Lifetime is longer than 10 to the 15th. If you put everything together that's known, the lifetime of the proton is longer than 10 to the 33 years. 10 to the 33 years is the bound on the half-life of the proton. Once this theory came out, it was immediately evident that experimental physicists should be trying to detect proton decay. The way to do it is to take 10 to the 33 protons and wait for one of them to decay. 10 to the 33 protons, how much is that? 10 to the 33 protons. What's the mass of 10 to the 33 protons? 10 to the 23rd protons is a mole of hydrogen. So this is 10 to the 10th moles of hydrogen. Big vat or big swimming pool.
By 10 to the 8th?
What did I, sorry, what?
You got a G to the 4th, doesn't that give you a 10 to the 8th?
It does, but that's right. G to the 4th is a small number, but nowhere's near. Remember, we should, nowhere's near the required.
I'm saying it's 10 to the 25th or so. If G is about 1 over 100, then you get to kind of take.
Why are you measuring in years? What should you be measuring in? Light, yeah, the light transit time across a proton.
Yeah.
So it's got to be a small number, right? The expected lifetime, if everything was of order 1 in proton units, would be the transit time, light transit time across a proton. Don't ask me how long that is. 10 to the minus 15th meters, 15 and 8 is what? 23, 10 to the minus 23rd seconds. Did I get that right? 10 to the minus 23rd seconds is the benchmark number. Okay? 10 to the 33 years is the observational bound. Big number in between. G to the 4th, not important. Right. Okay? The only thing that can save us is m to the 4th, if m is big enough. Okay. How big does m have to be in order to be consistent with the 10 to the 33 years? The answer is about 10 to the 16th GeV. If this number is 10 to the 16th, let's see, is that right? 10 to the 16th, 4th is 10, yeah, that's the right number. 10 to the 16th GeV is the minimum bound on the mass of the X and Y bosons in order that it not conflict with proton decay. Now, is that a ridiculous number? No, I don't think it is a ridiculous number. First of all, it is, what is it? It's 3 orders of magnitude smaller than the Planck mass. So it's not above the Planck mass. That's a good thing. 3 orders of magnitude below it. But there is another factor that makes this very, very tempting. We've discussed it before. It's the running of coupling constants. The strong, weak, and electromagnetic coupling constants are not numerically the same. The electromagnetic is somewhat with appropriate adjusted various factors that you, for the group theory, just for the group theory, in order to compare SU5 with SU3 cross SU2 and so forth, there are some numerical factors, numbers like 3/8, trivial numbers. But simply stated, with appropriate conventions, all of the coupling constants in a unified theory should be the same. But SU3 cross SU2 cross, SU5 is not a symmetry of nature. It cannot be a true symmetry or even approximately a symmetry of nature. Why? Because of the enormous difference between the necessary mass of the X boson. The X boson exists in the same multiplet as the gluons, the W boson, and the photons. Okay? It exists in the same multiplet, and if the symmetry was an ideal unbroken symmetry, they would all have the same mass. Well, the photon is a good deal lighter than either the Z or W bosons. The gluons, their mass is 0 in the formal quantum chromodynamics, so it's like the photon, and now the X boson has to have this gigantic mass. That means the symmetry is broken, spontaneously broken. What is it when
I guess if it's not broken, then all of these bosons are massless.
Then all the bosons are massless, right? You could arrange for them to all have the same mass and not be zero, but that's not really right. Okay. What is it that gave the W boson a different mass than the photon? It was the spontaneous symmetry breaking, or the Higgs phenomena, that created a different mass for the W than the photon. And at the same time, it broke the SU3 cross SU2 cross U, the SU2 cross U1 symmetry. What's necessary is a Higgs-type phenomena, a different one that splits this from this. That splits this from this, breaks the symmetry drastically between this block and that block. And it is that symmetry breaking which would account for the big mass difference between the X and Y bosons on the one hand and the gluons or the Z. To first approximation, all these particles are massless. They have, the biggest mass here is only 100 GeV. We're comparing things with 10 to the 16th GeV. So to first approximation in this kind of theory, these are all massless. In fact, everything on the blackboard is massless. And the X and Y bosons have this large mass. That's the theory. I mean, I'm not saying it's true. This is to be tested. So with a mass of 10 to the 16th GeV, you're fine. It's OK. All right. Now, what other evidence do we have for a scale of 10 to the 16th GeV? We have a couple of other pieces of evidence that the scale of 10 to the 16th GeV is the scale of unification. What does it mean, the scale of unification? It means energies which are high enough that even the mass of the X and Y bosons can be considered to be zero. In other words, if the mass of the X or Y boson is 10 to the 16th GeV, or 10 to the 15th, somewhere between 10 to the 15th and 10 to the 16th, then well above that energy, let's say 10 to the 18th GeV, processes are insensitive to the mass of the X and Y bosons. They can be treated as massless in that limit. In that limit, the difference between the X, Y bosons and the Z and W and so forth is not important. In other words, above those energies, the symmetry is a good symmetry. Right? Is a good symmetry. So the question is, at what point at what energy scales does the world appear to be SU5 invariant? All right. There's some answer to that, and the answer goes as follows. I've told you several times that coupling constants are not constant. They depend on energy scales. The coupling constant that you see in quantum electrodynamics, the fine structure constant, actually depends on the energy of a process. It runs. That's the terminology. Coupling constants run. They vary. If you plot, it's traditional for, well, not just traditional, useful, instead of plotting the coupling constant, plotting 1 over the coupling constants. And you plot them at laboratory energies. In this direction, you have energy, and you plot the measured value of them at laboratory energies. This is really logarithm of the energy here. If you plot the value of the 3 coupling constants, which 3? SU3, cross SU2, and U1. The 3 coupling constants, they are 3 numbers. The biggest value of 1 over g squared would be for the U1, in other words, the weakest of the interactions, the electromagnetic. Next, the SU2, and next, the SU3. Okay. Now you plot how they run with energy. Now, run with energy, how do you plot it? You don't measure it. They run logarithmically, very slowly. You calculate it. You calculate it from the theory. You have the particle content. You have the Feynman diagrams. Particular Feynman diagrams go into the running of these coupling constants, and you plot them. And what do you find? You find that they do something like this. Now, that's approximately what they do. They more or less come together, look as though they're going to cross, and what you'd like is that they all cross at the same place. What you'd like is that there is one place where they all come together, and at that point you would say, that's the unification energy. That's the energy where you've gotten high enough that beyond that energy, all three coupling constants are the same. Now, why do they run differently? Why do they run differently? If there's a symmetry between these three coupling constants, why do they run differently? And the answer is that below this energy, the symmetry is broken. Above that energy, the symmetry is restored. So that's the picture that you would like, and you would like them to all coalesce simultaneously. They don't quite. In fact, they miss each other by a fair amount, but the tendency is certainly for them to come together. I can't remember whether this one crosses here or this one crosses here. It doesn't matter. They do miss each other by an appreciable amount. Right? Nevertheless, you take them, aim them, do the calculation, and you find out that there's, if you allow 15% error, you would find that these things cross at an energy of, guess where? The same energy, 10 to the 16th or 10 to the 15th GeV. So the implication is that if you believe this theory, the unification scale really should be 10 to the 16th GeV, and then the mass of the X and Y boson would be about that. This is the reason, yeah.
If in this Feynman diagram for proton decay, you replace the free U with a free D,
yeah,
then you're looking at neutron decay.
Yeah, but neutron decays by beta decay so fast it doesn't matter.
So if you look at the products of that, does the X boson get involved at all?
Wait, say it again?
Replace the U on the right with a D. Then
Yeah.
Then you're looking at neutron decay.
Yes, but there's another mechanism for you. Right. So you would.
That happens. The free neutron will decay.
Yeah, but not by this mechanism. It doesn't decay to a let's see, this would be. It doesn't decay to a pi meson and a positron. That would have been noticed. It decays to a proton, a neutrino, and an electron. Okay, so a completely different process. Yes, but you're right. You could imagine a world in which the neutron was stable with respect to beta decay if the neutron was a little bit lighter than the proton. Imagine that the neutron was this would be a disastrous world. You wouldn't like it. But the neutron would be stable, the proton would beta decay into the neutron. But now take the neutron. The neutron would decay by this process, but again, the lifetime could be very long. Right, so just by juggling the masses of the proton and neutron, you could imagine a world in which this long lifetime would apply to the neutron, not to the proton. All right, that's pretty much it. We're about out of time. That's pretty much it for what a grand unified theory is. The only last thing I promised to tell you is what the relationship between grand unified theories and supersymmetry is. Not a lot. I mean, no tight relationship. One doesn't imply the other. But what is true is that if you add all of the superparticles into the calculations for the running of the coupling constants, then you do much, much better. Within about 1%, these do cross at the same place. Is this an accident? Is it a 1% accident? Who knows? In any case, this is why there is excitement about supersymmetry and about grand unification. Grand unification is a quite beautiful idea of fitting all of the particles into a single multiplet like this, into a single group structure like this. In a slight extension of this theory, incidentally, in the theory based on the group O10, which is a little bit bigger than SU5. SU5 fits into O10. In O10, all of these particles exist in a single multiplet, the 16-dimensional representation of O10, along with one other particle, an antineutrino, or the right-handed neutrino, as it's usually called. But that's a separate story. Okay, that's the idea of grand unification, its connection with supersymmetry, which is not theoretically terribly strong, but empirically there's some reason to find it attractive. Proton decay experiments are ongoing. The lifetime is getting, every year the lifetime gets a year long. No, that's not right. No, that's actually not right at all, is it? But every year the bound goes up. In supersymmetric theories, the lifetime calculation is different and can vary all over the map, but it never gets any bigger than about 10 to the 35 years or something like that. It's difficult to make it bigger than 10 to the 35. In the standard model, you can't make it short with this kind of number for the unification scale. You really can't make it shorter than about 10 to the 32 years. Nothing you can do can make it shorter than that. In supersymmetric theories, it could go from a fraction of a second to 10 to the 36 years, and with various assumptions about things. So there is no real prediction in supersymmetric theory for the lifetime of the proton. All right. May all your protons be stable until the autumn quarter. And I wish you a fine summer. Let sunshine shine. And
For more, please visit us at stanford.edu.